This video will deal with climate issues and will address the 4 points shown on this first slide. The first of these is the question, is the Earth's climate changing due to man's activities? Does the burning of hydrocarbons cause planet warming? And if so, do we need to make changes for the planet's welfare? Now, the United Nations Intergovernmental Panel on Climate Change has been attempting to answer this question since about 1988. They have studied global warming, which has now become termed climate change. The fifth annual assessment report, AR5, was issued toward the end of 2015. That report and all of the reports prior to that have warned of catastrophe ahead for the Earth unless we make some drastic changes in our energy consumption behavior. This video will deal principally with the evaluation of this United Nations AR5 climate modeling result. They've modeled the Earth's temperatures, history, and they've shown the results we'll see here briefly in the next few slides. My conclusion is that their models very poorly fit past Earth temperature data. And I will close at the end of this video with another model, so-called Cyclical Temperature Model, that fits what is happening. And the United Nations Intergovernmental Panel on Climate Change to date has neglected this model and this large set of data behind it. I do not. Now, the UNIPCC models are being developed by many different entities, and they are of differing complexity. The simplest model initially that they used involved only an energy balance between the Earth and the Sun, and that was found very quickly to be inadequate. So in the years since, they have developed complex models and merged submodels into a very big model. Submodels such as of the atmosphere, how does the atmosphere behave, how do the oceans, land, sea ice, clouds, and this list of sub-areas that one could study. And as the result of studying each one of these sub-areas, a number of models were put together with the assumption that the merged sub-models that seem to work pretty well will model the whole. We'll see that that does not work. Now, these models get complex and costly to run on computers, but they require a large amount of computer time, but this computer time has been spent, and we'll see the results of that in the next slide. Now, here is the results of the AR5 modeling. There are a whole bunch of curves shown on this slide here, and the next slide will simplify it and show you the important parts of this curve that you need to see. But let's just look and see what we're seeing. First of all, the solid black line here is what is believed to be the measured average temperature of the Earth since about 1860 to present. So that's Earth measured temperature data. That is the goal, to fit that with a model. Now, the whole bunch of other curves on here, the fine curves that are shown here is kind of a jumble. Those are the results of 42 different models that were done by various scientific entities around the world to try to model this black line of the measured Earth temperature history. The solid red line that's sort of easy to see here is the average of those 42 models, and it's believed that that solid red line is the model that the UNIPCC AR5 workers have determined to be their best model, being the average of the 42 models. And so the red line compared to the black line is what we're interested in evaluating here. You can see here that there's some deviations, and I'll explain that in the next slide, but here's the Earth's temperature history in recent years, and here's what the model says should have happened, and they don't agree particularly well. Now, here's a simplified view of the same data we just looked at to give you a better feeling for what's going on in terms of data and model. Again, the black curve here is the measured Earth temperature history, whereas the red curve is what the UNIPCC believes is their best model fit. Now, to the naked eye, it may look like a reasonable fit, but from a nonlinear modeling aspect, which I will discuss in the next few slides, it is a very poor fit indeed. In fact, what happened with this UNIPCC study was that all of these whole bunch of 42 models ended up being down in this area. And what they did is they took the average of those 42 and then they artificially moved it up to agree in this area because it appeared that that agreed pretty well. But even doing that, you can see that there are a couple of areas where there's a significant disagreement, in particular between 1900 and 1930, and I'll explain that a little bit in the future, and the most recent history of the Earth since about 1998, in which the Earth's temperature is sort of essentially leveled off, whereas the model predicts that it should have increased and that it would continue to increase. And those are pretty iffy scientific extrapolations and results. Let's take a brief look at just that Earth temperature data line, the black line, and see some interesting trends that occurred while those temperatures were being measured over time. You can see that from the earliest time, the annual average Earth temperature sort of increased along this line here, but then at about 1940, it basically leveled off. Between 1940 and 1970, the Earth's temperature did not continue to rise, but instead it leveled off. Well, the climatologists at the time, having observed this trend, believed that what was going to happen in the not-too-distant future was an ice age. They thought that this was a precursor to an ice age that was about to happen. And what happened in April 22nd, 1970, as a result of the fear of an impending ice age, the first Earth Day was declared. We celebrate Earth Day every year since, but it's rather ironic that it initiated as a result of the fear of an ice age, whereas today it's the fear of global warming or climate change. We can see that what happened after 1970 is the temperatures continued to rise, sort of following this trend before, but it continued to rise. And that since 1998, as I've already mentioned, it basically leveled off. And if you will be consistent in terms of interpreting this recent temperature data, you might expect that you'd call for an ice age, but that's not happening. Instead, we're talking about that as being something related to global warming or climate change. Now, again, I've mentioned this already, but this is a good place to see this, that the most recent years, even though they're leveling off, the most recent years in the most recent decade or two are the hottest on record. They're hotter than anything that happened before it. So that can be presented by a global warming enthusiast as the evidence, just kind of a common sense evidence that global warming is happening, because every year is getting to be hotter in recent times than it was in the distant past. Well, I'll show you, and when we look at this cyclical model, that that's not the case at all. In fact, the fact that we have the highest temperatures currently relative to the past is not anything to be alarmed at. In fact, the increase is the total increase that we have here over this time period is about 3/4 of a degree centigrade, which is not very much over all of that length of time. And again, it's not going to be a disaster ahead. I'll show you that when we look at this cyclical temperature model. So we need to look at 4 or 5 slides here and just look at what this modeling business is all about. It's something that mathematicians, engineers, and scientists do all the time, to have data in hand and to try to evaluate it with a math model. Let's just look at briefly the 2 rules that are involved in that. One, first of all, you must have data. If you're going to have a mathematical model or scientific model that you're going to try to use to extrapolate into the future, you have to have data to which to validate or compare to your model to show that you have a good model, and therefore you can extrapolate into the future. In the case of global warming and climate change, we have the temperature data, so there's no problem with point number 1. Point number 2, however, is that you must ensure the model very closely fits the data, and that's really the kick here, very closely. Even if you see something to the eye, when you look at it and say, oh, that model fits pretty well, as you might have thought the first time you saw that AR5 model versus the measured temperature history of the Earth, you might have thought, well, hey, that's pretty good. It sort of covers it. Well, it turns out that that's not really the case in terms of a discipline that we call non-linear modeling, and I'll explain that in the next few slides. But basically what one needs to do, you need to do an extensive analysis of your fit to ensure that quality. And then and only then, when you've done that analysis, can you have future predictions that have any validity whatsoever to predict, in our case here, what the future temperature of the Earth will be. Now, there are two types of gross mathematical models that one deals with in the real world. The simplest of these is we call a linear model. It's simple, it's accurate, and there's no question about future predictions. Here's a set of computer-generated data versus time of some parameter here, just showing it linearly or increasing in a line. A very silly example of this would be if someone is born in the year 2000, their age is a linear function of the date. In 2010 they'd be 10 years old, in 2020 they'd be 20 years old. So that's really a kind of a silly example. And there are a few things other than age versus date that are linear in this world, but many of the things in the world are what we call nonlinear. And they are therefore nonlinear models that are very complex, and they need to be very carefully analyzed before you can extrapolate into the future. The Earth's climate behavior is a highly, extremely nonlinear model, and therefore we have to follow the nonlinear modeling rules that I'll show you in a minute. I've shown here some nonlinear data. It's not linear, it's not just going up in a straight line. It's nonlinear, it's bending over here. And also you'll note there's some scatter in these data. It's not as smooth as this data here, this linear data. There's some scatter. And this is a computer-generated set of data that I'm going to use for illustration purposes, and the variation that you see there is random error. And I'll talk a bit more about that. I've taken a generated data set and I've given it mathematical random error, which is the type of error that we see in every experiment, every measurement that we make, whether the instrument that we're using is a little bit irregular at times, or whether the user of the instrument, the person taking the measurement, is not exactly accurate in every time he uses that instrument. So there's always this nonlinear data full of some amount of random error as shown in this plot. So let's look at this set of data, this second set of this nonlinear model. When we have nonlinear data, again, the same circles are shown here as the data that I've generated from the computer model and added random error to it. We can do something with the data and a model, which is called nonlinear model fitting, or using what we call a nonlinear regression program. We have a computer program that can take the data and can take a model and force the two of those to fit by varying some constants in the model. What I've shown here is model A. It is a simple function of time here of a constant A times time divided by a constant B plus time. So the constants A and B are parameters that will define the curve of that model A. So we take those values, those constants A and B, and we put them in the data and this model into a nonlinear regression program, and that program tells us that the parameter A should be 2.762 and the parameter B should be 1.809. And it resulted in the solid red curve fit to the data and the open circles that were shown here. And to I, and it turns out to the scientific analysis, that is an excellent fit. In fact, since it turns out that this model here that was regressed, that was determined from the data, is very close in agreement to the actual parameters that were used to generate the circles in the first place before the random error was added, A of 2.75 and B of 1.75. These values are reasonably close to that. Now what a nonlinear regression, nonlinear mathematician would need to do would be to not only have that fit, but you have to look at some other parameters, the most important of being something that we call the residual. And this is a plot of this parameter called the residual, in which we have the difference between the calculated and observed divided by the observed value. And what we're looking for there is to have these points just kind of randomly distributed about this axis from 0 to plus and minus a little bit. No regular pattern here. And in fact, this shows no regular pattern. Everything looks excellent in this area. That is model A, which is the correct model, and our analysis of the data with random error added relative to this model gave us the correct answer. Now let's look at a same set of data again, the open circles, and let's fit it to a different model, model B. This is a more complex model. It's got the four constants C, N, D, and E. It's just shown a little bit more complicated function here. And again, we take the data and we do a nonlinear regression to it, and we get values for these four constants that will give us the solid green line shown in this figure. And the fit to the untrained eye looks pretty good, pretty reasonable. And to the trained nonlinear modeler, it has a flag, and that flag is in this last part of the data, noting that the data seem to be in a regular way below the curve, that the data are saying that and the curve is a higher value. Again, if we look at these residuals versus time, and the green circles here are those residuals, the difference between the calculated and observed divided by the observed, we see that it looks pretty good up to about 20 years, but the flag that's raised and the problem is that all these residuals are positive in later times. And that is an indication of the nonlinear modeler that there is a significant problem with this model. So this is not a good model, though to the eye it looks sort of reasonable. Well, let's just play the game with what would happen if we use both of these models to extrapolate into the future. Here is the result of, again, the data are shown in this area here, up to about 25 years, I believe. And if we take model A and extrapolate it, again, that's the correct model. That's the model from which the data were generated. It shows that it's basically leveling off, or actually I think it's declining a little bit with time. Look what model B does. Model B that sort of looked to the eye looked pretty good, but in further analysis showed to be invalid, shows a great increase versus time, and that's not the correct way that the data was trying to tell us would happen in the future. It turns out that this is the same sort of a thing that we're seeing with the gap between the UNIPCC model for what the temperature should do and at least currently what the temperature is doing. Now that you know a little bit about this business of analyzing a data fit in a nonlinear sense by looking at the residuals, let's look at the residuals from that fit of the UNIPCC AR5 model to the Earth's temperature data. And here's a plot of those very same residuals. Again, the residual being the difference between the calculated value and the observed value divided by the observed value. And we can see some significant problems here. First of all, the residuals are very large. They should be at least within these two red lines here, the 10%. If it's an excellent fit, it may not be possible with the variations in Earth temperature measurements that we have, but ideally it would be within this 10% range here, plus or minus. But indeed it's quite a bit larger, but the more important factor is that same business that I told you about. Between 1900 and 1930, all of these residuals are negative, which is a flag indicating that there's an inadequacy in the model. And similarly, since 1998, all of the residuals are positive, and that is a flag that's saying that that model is not good. It needs to be altered in order to have that model be of any use whatsoever to extrapolate into the future. There is an additional model that explains the behavior of the Earth's temperature recent history, but also goes back prior to 1860 when we did not have any actual average Earth temperatures, but we have a whole wealth of indirect results. It turns out that if you go to the Arctic or Antarctic and drill a deep core of that ice that's on top of the land of that area, you will find that there are over 600 cooling and warming cycles lasting about 1,500 years each to be found by looking at the layers, the thickness of the layers, and the attributes of the layers that are found in those cores. And so in other words, we have 1 million years worth of Earth's temperature indirect proxy data found in these ice cores, and they exhibit 600 cyclical cycles in which the temperature goes up and down over the span of about 1,500 years. What is found is that every 1,500 years during that cycle, we'll see that in a few minutes, and more ideally, the temperature goes up 2 degrees centigrade, it drops back to the average Earth's temperature, and it goes down 2 degrees centigrade, and then comes back up to the average Earth's temperature. We'll see that in more detail. Now, here's one of the ice cores and taken from Antarctic. in which we see that there was a time in which there was a cooling, then there was a time in which there was warming, and then there was a time in which there was cooling. These epochs here, we'll see in a few more detail in later slides, there's something known between 913 as the medieval warming, and this ice core saw it. There was something between 1300 and 1850 known as the Little Ice Age, and this ice core saw it. So that's ice cores that see about a 1500-year cycle, 2 degrees centigrade up, 2 degrees centigrade down above around the average Earth's temperature. But it turns out that there are a bunch of other independent scientific disciplines that see the same thing. I just described you what Arctic ice cores and Antarctic ice cores see. If you go offshore and drill a sediment core from the near shore sediments that have been deposited over time, you'll get the same sort of a number. If you look at coral reef composition, peat bog history, iron dust, tree rings, and about 3 or 4 additional independent scientific areas that find the same thing, and what they all find is that the Earth has a cyclical temperature history, and the range that they find is this range happens between every 12 to 1500 years, and it's 2 degrees centigrade up, 2 degrees centigrade down during those cycles. If you'd like to get additional information on that, I suggest this book, Unstoppable Global Warming Every 1500 Years, and you can see the various sources of this information, but it is indeed an interesting set of so-called proxy data that describe what's going on in the Earth in the past, and I believe what describes what's going on the Earth today. So basically, showing a very simple sine curve here, is that the Earth goes, in this case from the ice cores, a 1500-year cycle. Starts out somewhere at the average Earth temperature, which is about 14 degrees centigrade, and it goes up 2 degrees, then it falls back to the 14 degrees centigrade, then it goes down 2 degrees, then it comes back up. That's the result of all of these various technologies find somewhere between 1500 and 1200 years that this cycle repeats itself. Right now, and we'll see this in more detail in a minute, right now we're about at this point in the upswing of this cycle, about 3/4 of a degree up in that particular location on this cycle. Now, rather ironically, at least the ice cores themselves, having been frozen with an atmosphere that's present at that time, when you analyze these ice cores, let them melt and measure the carbon dioxide content of the atmosphere at the time, you find not only that there are certain levels of carbon dioxide in the past, but you find that this carbon dioxide goes exactly contrary to what the UNIPCC is saying. In fact, what they find from these ice cores is that the carbon dioxide buildup increases after the cycle starts to cool, not before. What the UNIPCC has contended is that this buildup occurs here, which causes the global warming to happen. In fact, what they found is exactly the opposite from the ice cores, and this needs to be explained. Now, so let's take a closer look at this cyclical model, and I've shown here a relatively complicated slide, but it's got 2 different curves on it. It's got a 1200-year cycle, and it's got a 1500-year cycle, shown as just a very simplified sine wave from trigonometry, a sine of the time, showing this plot. And I plotted on this the same temperature history data from 1860 to present, and you can see that it agrees pretty well with the upward trend there shown on this 1200-year cycle. And in fact, another thing that happens as a result of this visual fit is that you can see a comment I've already made, that if we indeed are on this upward cycle, our 1200-year cycle, then indeed the latest years should always be the hottest on record. And in fact, up to the year about 2250, which is right about here, we should have increasing Earth's temperatures as we get to this 2 degrees centigrade above the average Earth temperature of 14 degrees centigrade. And it's going to take 235 years from now before that happens. At that point, we will have declining temperatures, have another ice age, and we'll repeat this cycle endlessly. Now the UNIPCC predicts we'll get that 2 degrees centigrade in 50 years. Not only that, but that the temperature will continue to rise thereafter. Now the fact that this does not agree absolutely with the sine wave here, down in this area here, is nothing to be concerned about, because this sine wave is indeed a very ideal approximation. As you saw in that ice core plot, that it's a little bit more complicated than that. So I take this as being a very good explanation for what's going on in terms of the Earth's current temperature history. What is further proof that this is probably the best explanation, or at least it needs to be looked at by the UNIPCC and then explained why it is not, if it's not indeed a good fit, is if you take this 1200-year cycle and 1500-year cycle and take them back for an entire cycle. Here's what it shows should have happened. And indeed, what it shows that between 1300 and 1850, there should have been a cooling period known as in history as the Little Ice Age. And indeed, in the time before that, there was between about 900 and 1300, there was something called the medieval warming. Now, there are historical anecdotal data describing these two things. For example, during the medieval warming period in northern Greenland, the Vikings were able to grow food crops, whereas today it'd be impossible since it's totally covered with ice and snow. So there was indeed historically a warming period which had very significant different things going on in the Earth. As interesting is the Little Ice Age. This Little Ice Age occurred, and there's anecdotal data to say strange things that happened there. For example, in the Thames River in London, England, froze over 22 times, totally froze over 22 times during this ice age. And as late as 1814, there is reported total freezing of the Thames River, and the fact that they held ice carnivals on that river and having booths and circus clowns and all these sorts of things going on the frozen river during that time in 1814, and an elephant walked across the Thames River as a result of that last ice event in 1814. Since that time up until today, the Thames River has never frozen over again. Anecdotal data that show that this fit here with this sort of a cyclical model is the thing that describes all of the things we know about the history. Couple that with the fact that the UNIPCC AR5 model fits poorly from a nonlinear sense. I believe that this cyclical model is indeed the best model to explain what's going on in our world today. Now, just in brief summary, you've already said a number of times that the UN models significantly overpredict warming during the last 15 years as well as this period, and the residuals are extremely poor. Therefore, that model is not only not good, it's not in any way adequate to extrapolate and tell us anything about what's going to happen in the future. What needs to be done is their models need to be brought into agreement with their data, and they can't change the data, but they can improve their submodels, or they can do nonlinear regression to find a fit that gives the best overall fit of all of these areas, not just the place where they artificially cause it to fit. And in reality, I'm a scientist, an engineer, and what these climate modeling scientists need to do is to honor what we call the Socratic principle of science. That's something that all of us who work in science and are committed to do, and that is to follow the data wherever it may lead. In this case, the data show that their models are not good, and it shows that this cyclical model is capable of explaining not only what's currently going on, but past epochs that we've seen in the thing. And my advice to the UNIPCC is include this cyclical model in, at the very least, your discussions, and present whatever data you have to show that perhaps it is not a good model. Thank you for listening.